right? In the case of a ball, obviously you cannot see the details of it. You can say, yes, it is accelerating. If that's the case, you would come up with a theory that would give you a number that you can measure. If your theoretical numbers match the experimental numbers, then the theory is good. If your theoretical numbers don't match the experimental numbers, either your math is wrong, or your theory is wrong, or your observation is wrong, one of those. So, using the scientific method, what do we have? You got the observation. You have to have a theory that's going to make numeric predictions. Now what you need to do is you have to test the theory for further either experimentation or further observations. Experiment is going to give you numbers. The theory will give you numbers. If the numbers match, the theory is good. So, science is a numbers game. Science is the whole purpose of mathematics is to make numeric predictions. So this is going to be 3, 4, 7, 4, 6, 7, 1. Okay, so that's a number. So this is going to be 5.3474, 6, 7, and 1. I'm going to rewrite the number one more time. And this time, I'm going to take the number up to 7. And then I will rewrite the same number one more time. All right, so I'm going to rewrite the number one more time. And that's it. Notice that as I'm rewriting the numbers in this direction, numbers are becoming a little bit less accurate. As far as the accuracy is concerned, this one is the most accurate. And as far as the accuracy is concerned, this one is the least accurate. In this class, because this is physical science for non-science majors, and because of the simple reason that none of you will be working for NASA at any time soon, the sort of accuracy that we're going to go for will be the least accurate. All right, so as long as your numbers get up to this point, I'm going to be perfectly happy with it. Now, in terms of numbers, the numbers could be really, really big, or they could be extremely small. Speaking of big numbers, the mass of the Earth, for example, is a huge number. It's 5.98 times, okay, instead of writing it like that, let me just write it a little bit differently. All right, so 5.98, let's keep it like that, times 24 kilograms. All right, so which means that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You got 20. 1, 2, 3, 4. All right, so this is a big number expressed in terms of kilograms. What we need to do is if the number is extremely big, like this, the number needs to get crunched down. So you have to take the number and you have to crunch it down to something which is easier to read. And of course, it doesn't take up as much space when you're writing it down. Also, it doesn't take up that much time just writing it down. So what you need to do is count the number of decimal places between the original number and the point right after the first number, and then just express it in terms of an exponent of 10. All right, if the number is big, you kind of crunch it down using something called the scientific notation. So this is known as the scientific notation. So scientific notations are common. Scientific notation is the way we express extremely big and small numbers. All right, so this one is one example of it. The smallest number in physics is known as the Planck's constant. It's a quantum number. Let's copy that down. So it's h, and this is going to be a very small number. And physics is going to be accurate to this number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30, 1, 2, 3, 6, 6, 2, 5. I think this is good enough. So what I'm going to do is I'm going to grab the decimal from here and place it right after the first number here. All right, so this is a really, really small number. It's very close to 0. All right, so h is going to be 6.625 times, we got 34 decimal places in between. Now I'm going to place a negative up front, indicating that this is a small number. All right, so the small numbers, as well as the big numbers, will be expressed in terms of the scientific notation. So extremely small numbers and extremely big numbers will be crunched up, or crunched down in this case, using scientific notation. All right, coming up with a number itself is not good enough usually. We have to do a lot more, because when you come up with a number, the numbers need to be expressed using units. Numbers alone don't mean anything in physics. It's not like math or physical science for that matter. So what we will need to do is we need to express these numbers using units. So that's the next topic that we need to discuss. In the United States, we use something called the British unit system. All right, so in the United States, we use the British unit system. Case in point. 1 foot. How many inches? It's 12 inches, right? How about a mile? Most of you guys would know that 1 foot contains 12 inches. And most people would know that 1 mile contains about 5,000 280 feet. Unless you look this up, you wouldn't be able to. You wouldn't be able to know this. 1 mile contains 5,280 feet. So they're back on. Okay, so this is the British unit system that we've been discussing. And British unit system is the one that we use in the United States. The problem with the British unit system is 1 foot 12 inches. Why 12 inches? Why not 14 or 15? Why not 10? 1 mile is 5,280 feet. Why not 5,000 feet? The numbers are weird. The metric unit system, which is otherwise known as the standard international unit system, does away with that complication. All right, so this is known as the standard international. Standard international. Standard international, otherwise known as the SI unit system. So the initials for the metric unit system. In terms of distances, obviously the base unit is going to be a meter. You can take a meter and break it into 100 smaller pieces. These are known as centimeters. You can take a centimeter and break it into even smaller units, which are known as millimeters. Or you can take 1,000 meters and call it a kilometer or a kilometer. All right, that's it. So the base unit is going to be a meter. Meter can be broken into centimeters. Centimeters can be broken into millimeters. Meters can be expressed in terms of kilometers. Kilometers can be expressed in terms of meters. That's it. All right, so this is what we use in the United States, and this is what the rest of the world uses. Which one is more accurate? Which unit system is more accurate? When I ask you that question, almost forces you to come up with an answer. You're thinking, oh, I think the standard international is probably more accurate because that's what the rest of the world uses, right? Not necessarily, guys. Both unit systems are just as accurate. The smallest unit here is a millimeter, which is the same as 1/20th of an inch. All right, so accuracy is not the question. Kamara likes the United States better. Give your subsequent. All right, so which one is more accurate? Both of them are equally accurate. If they're both equally accurate, why then the rest of the world uses that? The reason why the rest of the world uses that is because of the numbers. Look at these numbers. Everything is a factor of 10. Here, you got these weird numbers. This is a weird number. This is a weird number. All right, you can do this in your head. This requires memorization. Only 3 countries still use the British unit system. Obviously, the United States is one of them. Canada is not the second one, and Britain is not the third one. If you go to Canada, they will have they use the metric unit system, but they will have the British unit system on the side, just in case if there are people from the United States. All right, there are 2 other countries whose names I don't recall. They're just insignificantly small. All right, so this is going to create some problems in terms of the unit system. This is what we are used to. British unit system is what we are used to, but we have to express things in sciences using the standard international unit system. Case in point, if I'm driving my Ford Tempo in a 30-mile-per-hour zone at a speed of 26.78 meters per second, would I get a ticket? What I'm asking is, am I going faster or slower than 30 miles per hour? So I'm driving my Ford Tempo, and my speed is 26.78 meters per second. So my question is this faster or slower or the same as 30 miles per hour? So that's what I'm asking. Would this be faster, slower, or the same? It's 30 miles per hour. All right, so if I'm going at 26.78 miles per hour in a 30-mile-per-hour zone, would I get a ticket or would I be okay? You don't know, right? And there's a reason why you don't know, because you don't understand the conversion. So 26.78 meters per second. How fast is that in terms of miles per hour? So for us to be able to figure that out, what we need to do is we need to use a conversion factor. We need to have a speed conversion factor. Conversion factor for the speed is the following. 1 meter per second is the same as 2.24 miles per hour. This is known as a conversion factor. If you know the conversion factor between meters per second and miles per hour, the rest is straightforward. It's easy. You will get to do a bunch of conversions from time to time. Initially, you will do tons. Later, it doesn't matter. And you will find the conversions in the formula sheet. All right, so this is known as a conversion factor. This is our conversion factor. All right, so if that's the case, 26.78 meters per second, expressed in terms of miles per hour. What could this be? All right, let's take a look. All right, the first thing we need to do is we need to express this in terms of miles per hour. So we will have to multiply this with a conversion factor. Speaking of multiplying things using a conversion factor, what you need to do is whatever the number that you see here, which is expressed using this unit, get that unit in the denominator. All right, so that unit needs to be placed right in the denominator. So meters per second is going to be here, and we will be converting to miles per hour. The next thing we need to do is the meters per second, find the unit in the conversion factor. So these are the same units. Grab the number and in front of meter per second and place it right in front of meter per second. You got your miles per hour located here, so this number is going to go there. All right, so that's what we'll do. So in front of this you have 2.24. In front of this you have 1 meter per second. And then the next thing you need to do is just get rid of the like units. So these units will cancel. So these two units will cancel out. And the surviving unit is the unit that we will get to use. All right, so which means that this speed is going to be 26.78 times 2.24 divided by 1 is going to be, it will be 60 miles per hour. That's it. So our speed is 60 miles per hour. Okay, so we got our answer. The answer is straightforward. If you're driving in a 30 mile per hour zone at a speed of 26.78 meters per second, you're going at 60 miles per hour. So this thing is definitely larger than 30 miles per hour. If you get caught, you will definitely get a ticket for that. Let's do one more example. All right, so that's our first example. The second example, just want to make sure that you guys know how to do the conversions. It's going to be related to the following. I'm going to come up with a speed. This time our speed is going to be 773 miles per hour. And let's express this speed in terms of miles per hour, meters per second. All right, so this is going to get expressed in terms of meters per second. So what is this? Okay. Now this speed means something if you're a physicist or an engineer. It signifies something. So the question is, what does it signify? What this speed signifies is the speed of sound. All right, so this is the speed of sound. This is the speed of sound at room temperature. All right, so if you're under this speed, it's known as subsonic. If you're over this speed, it's known as supersonic. That's 773 miles per hour. So what is this speed in terms of miles per hour? Okay, so once again, we will just do our conversion. Let me just grab this. All right, so here's the speed. And then let's apply our conversion factor to it. So this is going to get multiplied by the conversion factor. Once again, the unit that you see here has to be placed right at the bottom. So miles per hour. And then we're converting to meters per second. All right, so our conversion factor is located here. Conversion factor is right here. All right, so meter per second is going to have 1 in front of it. So we will have to place 1 here. Miles per hour has 2.24 in front of it. So we will have to put 224 right there. So that's how we will do this. So 1 meter per second is the same as 2.24 miles per hour. And once again, the like units will cancel. So this unit is going to cancel this one. So we'll get a cancellation between those two units. So if that's the case, our unit, our speed is going to be 345.08 meters per second. All right, so that's how we do our conversions. All right. So the convergence will require a conversion factor. And through convergence, we're going to be able to do convergence between the standard international unit system and the British unit system. And hopefully you will become rather good at it. So where do you find these conversions? All right, let's check to see where we can find these conversions. All right. Go to modules. Okay, notice that it says college physics formulas or formulae. Formulas, formulae, they mean the same thing. Just open this up. And then this is going to have all the formulas that we need. And a lot of it, all the formulas we need, and some more. We're not going to be using most of them. The stuff that you need, though, this stuff, the conversions. All right. So the speed that we were talking about, V, 1 meter per second is 2.24 miles per hour. and 1 meter per second is 3.6 kilometers per hour. So the only one that we will be using is this for the most part. All right, so now that you know where to find this stuff, let's get back to the lecture.